Lecture 2. You will require the outline for Lecture 2, straight lines. This is work you covered at school, so we are going to move with this a bit fast. A1, summary of work covered at school, equations of straight lines, the vertical line defined by x is equal to a, where a is a constant. Horizontal line is y is equal to the constant, say b. The point slope form is given by y minus y sub 1 is equal to m into x minus x sub 1. The slope intercept form, y is equal to mx plus b. So for all the letters were lowercase letters. For the general form, capital AX plus capital BY plus capital C is equal to 0, where the capitals A, B, and C are constants. Now, to summarize, the straight lines right? Your gradient intercept form from school is y is equal to mx plus k. Above they used y is equal to mx plus b, right? So in this case, you know that your m is your gradient and k the y-intercept, right? So we need to make a note of that. M is gradient, and your k is y-intercept, where the graph cuts the y-axis. Okay. We look at the case where if your equation is in the form y is equal to mx plus k, if m, the gradient, is positive, then the shape of the graph is going to be as indicated over there, right? In other words, it's going to be an increasing function. If m, the gradient, is less than 0, then you have a decreasing linear function, and that's going to be the shape. And you know that from school that m is equal to the change in y over the change in x. Okay, we now look at the general form of the straight line. That's ax plus by plus c is equal to 0, right? Capital A, B, and C, right? So you should know from, you can take the general form and By solving for y, write the equation in the form y is equal to mx plus k. Right from that, you'll be able to get out the gradient and the y-intercept. Right, if possible, in certain cases, we have special cases. You could have an equation like this. Y is equal to, say, some constant a, and we know this is a line parallel to the x-axis, right? You could, by solving sometimes for x, you could end up with x is equal to, say, some constant b, and this is a line. It's a defining equation of a line parallel to the y-axis. Okay, so that is your summary in terms of a flow diagram. We now move on to the next page, page 2 of the lecture outline. So let L sub 1 and L sub 2 be two straight lines, and we want to know what is the relationship between their gradients if the conditions, if you're looking at the conditions 2.1 and 2.2. Now you should note over here that our answers will depend on the following assumption: provided none of these lines is parallel to any of the axes. Right, this is our assumption. Right, so for 2.1, think about 2.1 and 2.2. You should know that if L1 is parallel to L sub 2, then the gradient of line L sub 1 must equal to the gradient of line L sub 2. 2.2, L sub 1 is perpendicular to L sub 2. In this case, the products of the gradients of these two lines, so the gradient of L sub 1 multiplied by the gradient of L sub 2 must give us -1. Let's look at example 1. A point R, capital R, points are labeled with capital letters. A point capital R, right, given by the coordinates x and y, moves along the line 2x plus 2y is equal to 16. if x decreases by 1 unit, what can you conclude about y? So the solution, 2x plus 4y is equal to 16, right? That's the general form. We want to get this to the slope intercept form. So 4y, this implies that 4y is equal to negative 2x plus 16. Dividing throughout by 4 implies that y is equal to negative half x plus 4. Therefore, your gradient m is negative half, which now implies that the change in y over the change in x is equal to negative half, right? We are looking at, we want to make a conclusion about y when, if x decreases by 1 unit, right? So rewriting this, your x is decreasing by 1 unit, so that means negative 1. The change in x is negative 1, right? So you can see from here, for equality, we must have the change in y to be half. So therefore, your y increases by half. Come on. Okay, that's the answer. So y increases by half. That's answering the question. Now, graphically, this is what happens. The situation, you've got your x-axis, right? You've got the y-axis. From the general form of the equation, if you want to find the x-intercept, you set y equal to 0. So you'll get 2x is 16, so x is equal to 8. That's your x-intercept. Your y-intercept set x equal to 0, 4y is equal to 16. So y is equal to 4. So your line is going to be like this. All right, that's your straight line. You can push it up. So when x decreases by -1, let's say it from say 8 on the from the x-intercept, when x decreases by -1, so you come 1 unit to the left, right? We want to find out what happens to y. That's what we're interested in, this part. You can see there that your y is going to increase, right? And from the calculation, it increases by half. So that's the picture there. We now move on to the next page, page 3, B1. What does mathematical modeling focus on? Now you'll find this on page 28 of the text, prescribed text. It's figure 28, right? You must see the steps 1 to 4. So we have a real world problem. That's the part in blue. What mathematicians do is they formulate a mathematical model, right? Then you solve that model, you end up with a solution of the mathematical model. So solving it is not just good enough. What you need to do is now interpret that solution of the mathematical model as a solution of the real world problem. And then you test it in the real world problem. That is how mathematical modeling is undertaken, right? You may have to reformulate the mathematical model. Unfortunately for you, in school and also at university, in many cases, the mathematical model is given. You have to just learn to solve the mathematical model and then interpret the solution. When you go into the real world, the mathematical model may not be there. You may have to formulate from the real world problem the mathematical model. So my advice to you is to work on that. 2, what type of mathematical models did you focus on at school? Right? You've come across linear functions, right? You've come across quadratic functions. Cubic functions. I'm going to write this in small, not in short form. Exponential functions. Right? Logarithmic functions, and so on. We're assuming that you know all the functions that you've come across at school, the types of functions. Now, the question, what is a function? It's a rule that assigns for every value of the input variable, right? Normally it's x. Only one value for the output y. Now the input variable is the independent variable. Your output variable is the dependent variable. Let's look at an example. Y is equal to 3x squared plus 2 is a function. We know that it's a quadratic function. It defines a quadratic function. We write f of x, read f of x in place of y to show the dependency of y on x. So f of x is equal to 3x squared plus 2, and f of 5, you'll have to replace wherever x appears by 5. So that's equal to f of 5 is equal to 3 multiplied by 5 squared plus 2, and you get the result. Note that this part is not f times x. We now move on to page 4, question number 4. Right? What is a linear function, and what are the uses of linear functions? So we're looking at what is a linear function and its uses. So the form is f of x is equal to mx plus a b, where your m and b are constants. Right? They can be used for, right, in the real world, simple depreciation, linear supply and demand, linear cost function, revenue function, and profit function. So we'll say linear cost, revenue, and profit functions.